You're strapped into a seat barely bigger than a phone booth, shoulder to shoulder with two other people you'll be sharing recycled air with for the next 7 months. The window beside you shows nothing. Not stars, not clouds, not Earth, just black. You knew this trip would take a while. That's the deal. But nobody really explained what a while means until you're 3 weeks in. The smell of your own sweat is permanent, and Earth is now a blue dot smaller than the head of a pin. Here's the thing people get wrong about going to Mars. It's not a flight. It's not even close to a flight. A trip to the International Space Station takes about 6 hours. A trip to the Moon takes 3 days. Mars? Even on the fastest realistic trajectory we have, you're looking at somewhere between 6 and 9 months, one way. And once you land, you don't get to come home for over a year. So how long does it actually take a human being to go to Mars, survive there, and come back? And what does that kind of timeline actually do to a person's body and brain? That's what I want to show you. In movies, Mars is close. A character straps in, there's a quick cut, and suddenly they're walking on red dirt. In reality, Mars and Earth are both orbiting the sun at different speeds, on different paths, and they're almost never close to each other. At its absolute closest, Mars is about 34 million miles away. At its farthest, it's over 250 million miles away. And because spacecraft can't just point at where Mars is and gun it, they have to follow a curved path called a Hohmann transfer orbit, essentially a long, fuel-efficient arc that intersects Mars's orbit at exactly the right moment. That means there's a launch window, and it only opens once every 26 months. We actually have hard data on this because we've sent robots on this exact trip multiple times, and they radio home the whole way. Take NASA's Curiosity rover. It launched on November 26, 2011, and didn't touch down on Mars until August 6, 2012. That's 253 days in transit, about 8.5 months, spent doing nothing but coasting through the dark. Perseverance, launched in July 2020, took just under 7 months to make the same trip. Same destination, similar trajectory, and still almost 7 months of just falling toward a planet. Here's the part that gets me. Curiosity wasn't just along for the ride. It carried an instrument called RAD-D, the Radiation Assessment Detector, and for those 253 days, it measured exactly how much cosmic radiation hit the spacecraft. The number it came back with was about 1.8 millisieverts per day. Multiply that out over a round trip, and an astronaut would absorb something like 0.66 sieverts of radiation without ever setting foot on Mars. For context, that's roughly equivalent to a full-body CT scan every single week for the better part of a year. And that's just the radiation. There's also your skeleton. In microgravity, astronauts lose bone density at a rate of about 1 to 1.5% per month, concentrated in the hips and spine. NASA's twin study, comparing astronaut Scott Kelly, who spent 340 days on the International Space Station, with his identical twin brother Mark, who stayed on Earth, found measurable changes not just in bone density, but in gene expression, eye shape, and even the length of Scott's telomeres. Now, some of you are thinking, okay, but that's the trip. Surely once you land, the hard part's over. Fair question. It's not. Because of those orbital mechanics we talked about, the 26-month launch windows. Once a crew lands on Mars, they can't just turn around and leave. The planets won't be lined up correctly for the return trip for roughly 500 days. That's almost a year and a half on the surface of a planet with no breathable air, average temperatures around minus 80 degrees Fahrenheit, and dust storms that can swallow the entire planet for weeks. In 2010, a Russian-led experiment called Mars 500 tried to simulate this. 6 volunteers locked themselves inside a sealed set of metal modules in Moscow for 520 days. No fresh air, no sunlight, no contact with the outside world beyond a communication delay deliberately built in to mimic the real thing. They weren't even going anywhere. They were just waiting, exactly like a Mars crew would have to. And speaking of that delay, depending on where Earth and Mars are in their orbits, a radio signal takes anywhere from 4 to 24 minutes to travel one way. Ask a question, and the fastest possible answer is 8 minutes away. In an emergency, that's not a phone call. That's a message in a bottle. So let's actually walk through what this looks like, start to finish. You launch during a roughly 2-week window that only comes around once every 26 months. Miss it, and you wait 2 more years. For the first few days, you're adjusting. Your inner ear doesn't know which way is down. Smells from your own body start to linger because there's no breeze, no fresh air, just filtered and refiltered cabin atmosphere. By week 2, the view out the window has changed for good. Earth isn't a planet anymore. It's a star. A blue-tinted point of light, indistinguishable from the others, except you know which one it is. Here's what modern people find hardest to understand. For the next 6 to 7 months, almost nothing happens. There's no scenery, no turbulence, no "are we there yet" landmarks. Just a tightly scheduled routine. Exercise for 2 hours a day on a resistance machine to slow the bone and muscle loss, maintenance checks on life support, and communication windows with mission control that arrive later and later as the gap between Earth and your spacecraft widens. Then, somewhere around month 7, Mars stops being a red dot and starts being a planet. You enter the atmosphere. Thin. Only about 1% the density of Earth's, just barely enough to heat a heat shield, but nowhere near enough to slow you down gently. This is the phase engineers nervously call 7 minutes of terror, because the entire landing sequence happens automatically, too fast for mission control to help, meaning everyone on Earth is just watching, waiting to find out if you're already safely down or already gone. If you make it, you're on the surface. And now the real waiting begins. About 500 days until the planets line up again for the trip home. So is this just permanent? Is a multi-year round trip the ceiling for how fast humans can ever get to Mars? Not necessarily. And this is where it gets interesting. The entire 6 to 9 month transit time is based on chemical rockets, the same basic propulsion technology we've used since the 1960s. But in 2023, NASA and DARPA announced a joint program called Draco, designed to test a nuclear thermal rocket engine in orbit, with a target launch as early as 2027. Nuclear thermal propulsion could theoretically cut transit time to Mars roughly in half, down to 3 or 4 months instead of 7. That sounds like a small change. It isn't. Halving the trip doesn't just save time. It cuts radiation exposure roughly in half too. It cuts the amount of food, water, and air a crew needs to carry. It shrinks the psychological burden of isolation. One engine change, and the entire risk profile of the mission shifts. And that one change cascades into everything else. A shorter transit means a smaller habitat is survivable, which means a lighter spacecraft, which means less fuel needed to launch it, which means cheaper missions, which means more of them. More missions mean more cargo pre-positioned on Mars before the crew even arrives. Habitats, water extraction equipment, fuel production plants that pull carbon dioxide straight out of the Martian atmosphere and turn it into rocket propellant for the trip home. Faster trips mean astronauts arrive less depleted, which means they can do more science, faster, in that 500-day window on the surface. Every saved month at the start ripples forward into the entire architecture of the mission. What could be one trip every 26 months might eventually become a sustained, continuous human presence. Think about that for a second. You've probably complained about a 14-hour flight. Maybe your skin started to crawl on a long layover, or you got antsy after 2 hours in a car. A round trip to Mars, even using the fastest technology we're actively developing, would take the better part of 3 years. Most of it spent either drifting through empty space or marooned on a planet, waiting for physics to let you go home. And yet, right now, on this planet, people are training for that mission, volunteering for it, competing for the chance to spend 3 years of their life, years they'll never get back, sealed inside a metal can, just to stand on red dirt for a year and a half. We measure distance in hours. They're about to measure it in years. Mars isn't far in miles. It's far in years of a human life.